Welcome to day 15 of the advent of compiler optimizations, and today we're going to finish off our talk about aliasing by looking at just another couple of cases where it may not be obvious what's going on. Let's head over to Compiler Explorer. So today I am going to implement a class, and this class is going to count the number of things. It's going to like an accumulating class. So let's get let's include span, and let's make this a template. We can actually see some C++. So we're going to be accumulator for type T. In fact, no, let's just call that total. This is going to be the thing that we're going to keep the total in, and we're going to say struct counter. We're going to have total, and I'm just going to initialize it like that, and then let's give it a count function stood span of we want sort of, let's just say we always take integers. We could always templatize this as well, but I'm just going to assume that we're taking integers. We're given a span, and then we're going to do our usual for auto lm over the span total plus equals lm, and I should really put some braces here, even though I probably wouldn't normally. Okay, I've stopped fighting the indentation. It's going to be 4 characters. That's how it's going to be. What am I missing? Oh, I need to put a semicolon at the end of the counter. Okay, so far, so boring. And also, no assembly's been generated. So we'll just quickly do a quick diversion as to why no assembly was generated, in case you've ever come across this in Compiler Explorer. When we declare a template, it's not instantiated. We don't have a type. So the compiler can't generate any code until it knows the kinds of types that we're using. Often that happens naturally as part of the rest of the code base, so somewhere else you might mention a counter of int or a counter of long or whatever, but we can actually force the compiler to instantiate a particular type using this slightly unusual syntax. So we're just going to say, hey, there exists a template class counter of int, and we can do the same, and we can make a template class counter of long. So now we're going to force the compiler to instantiate those two versions, that is, a counter that uses an int to keep its total and a counter that uses a long to keep its total. Make sense? Cool. So let's take a quick look at the two different implementations that have been made. We've got counter of int count over here on the right hand side, and it'll come as no surprise by now. We should be pretty good at reading assembly code. We're using an LEA instruction to find the end of the span, because the span is a pointer and a size, unlike the vector, which is 2 pointers. The span is actually a vector and a size, and so here we're taking the pointer and we're adding the size times 4 to it to get the end. And we're saying, are they the same? If so, there's nothing to do. Otherwise, we're going to loop around accumulating, and more importantly, the this pointer of this object. This is a member function of a template class. The this pointer is RDI, and we know that the total will be the very first thing in the structure. So when we read from RDI here, what this is doing, this is reading the current total into EAX, and then our loop, we're incrementing EAX around in a tight loop, and have we reached the end? If not, and interestingly, we're always writing to the total through the this pointer. So each time round, we're adding, moving on to the next integer, and then we're updating our total. Interesting. It's probably quite quick. We're reading and writing, it should all be an L1 cache, but it does mean that we are writing every loop iteration to RAM. Let's contrast that with the long version. So I'm going to scroll that to the top of the screen. Similar deal. Remember, we're still counting integers, we're just accumulating them into a long. So still calculating the end based on the size times 4. We are reading into racks, the 64-bit version of the A register, from the keyword pointer of RDI, because now our total is a long. We are moving, sign extending, that's what mov sx is. We're moving the integer from RSI into RDX, and that integer is only a 32-bit value, but we sign extend it to the full 64 bits. Then we move on to the next element, and then we accumulate into our racks register, the one that has the total in it, and then we keep looping. And then finally, at the end, we write out to our member variable through the RDI this pointer. And so the difference between the two of them, other than that sign extending, So I've got L9 here and L3 here are the two loops. So this is the long loop, and this is the int loop. Again, both accumulating integers, but into either an int or a long. What's going on here? Why is the int case writing to memory every single time, whereas the long case is not? You probably guessed. The clue was in the name of this particular episode, I guess. But yes, it's aliasing. Even though this is a member variable inside our class, this total, the compiler doesn't know and can't prove whether or not the int span that's being passed in overlaps with the inside of this class. You could imagine writing some code, terrible code, that took the int version here of the counter, instantiated it, and then passed to count a span that wrapped this total. And so the compiler has to assume the worst, and that every time it's reading and writing through the span pointers, it might be affecting the total or reading from the total. So that's why it's more expensive here. That doesn't happen when we use a long as the accumulator here, because the long can't overlap with the integer. That's not allowed by the type-based aliasing rules of C++. This is actually something that's caught me in real life. This is why I had this example to hand. I had a class which had a member variable and it was templatized in some way. And I noticed that when I used a particular type, it was generating poor code. And it took me a long time to realize that some of the member variables of that class were themselves subject to aliasing or potential aliasing. And as far as the compiler could tell, there was nothing it could do. It just had to read and write from those variables and not be able to hold them in registers during loops and such. So just another thing to watch out for. Anyway, that's it for aliasing. We're going to move on to something else tomorrow, and I hope to see you then.